everyone, my name is Monica. We're happy to have you with us for getting started with the basics of IP. In this series of videos, we will be moving step by step to help you gain a systematic understanding of all aspects of the field of data communications, including data networks, switching, security, routing, reliability, BGP, and multicast. Now let's get started.
This course contains a series of video classes, helping you learn the fundamentals of data communications networks, technology, and protocols systematically. Today is the first class, given a broad outline of some of the concepts we will look at. Today, we will look at some basic concepts related to data communications networking. We will also talk about the 7-layer OSI reference model, which is a very important point of reference for data communications professionals. Finally, we will learn how to use this model to analyze the processes involved in data transmission. First, let's look at some basic concepts of data communications networking. Data networks are made up of many commonly used devices, such as routers, switches, firewalls, and load balancers. Depending on the specific networking requirements, data communications engineers configure and commission these devices to set up a properly functioning data network. The basic function of data network is to allow any service nodes on the network to communicate with each other. The communication between devices must be controllable, reliable, and secure. In its simplest form, a network can consist of nothing more than two PCs communicating over a single network cable. However, even in this seemingly simple deployment, there is a lot going on. For example, which standards are being used? Which protocol are the two pieces using to communicate? Protocols such as the Internet Protocol, IP, are one of the most basic concepts required for understanding data networks. Protocols define the format of the units of data sent over networks, such as packets. How are packets physically transmitted? In our simple example, they are transmitted over the network cable. How are packets addressed? This depends on the protocol being used. In fact, the whole communication process is constrained, specified, and standardized by the different protocols being used. This is why it is very important for data communications professionals to grasp the concept of protocols and understand how they function. We must also fully understand the types of data carried on networks. Another very simple method to connect two nodes on the network is by using a somewhat outdated device called a hub. Many newer network engineers have never even seen a hub. So why are we mentioning it here? We mention it to introduce the concepts of collision and collision domain. Hubs implement a bus topology. This means that all of the network elements connected by a hub are within a single collision domain. Only one network element in each collision domain can use bandwidth to send data at any one time. Because collision domains significantly reduce network efficiency and reliability, preventative measures are needed. Switches are invented to solve this problem. Switches are different from hubs, improving on many of their shortcomings. Switches have many basic functions. As an access layer device, they are used to connect bottom-level network elements, such as terminals and PCs. They carry out data switching, including addressing for data frames. Each interface of a switch is a collision domain. Unlike with hubs, network elements connected to different interfaces of a switch sending data at the same time do not cause collisions. However, a single switch does often correspond to a single broadcast domain. This means that all devices connected to the switch also reside within the same broadcast domain. We can use the analogy of a room to better understand broadcast domains. If someone within the room starts singing, every other person in the room will hear the song, regardless of whether they want to. Similarly, if one node in the broadcast domain broadcasts a message, all other members of the broadcast domain will receive it, whether or not they need it. After receiving the message, a node may examine the data, find that it's not needed, and discard it. Broadcast is a method of transmission which is applicable to certain special scenarios. One of these is Dynamic Host Configuration Protocol, DHCP. In order to access the network, a host requires an IP address. IP addresses can be manually configured, or they can be dynamically obtained using DHCP. Dynamically obtaining IP addresses requires a DHCP value, and IP addresses are dynamically assigned using the DHCP server. To begin with, hosts don't know where the DHCP server is located on the network. They must send broadcast messages requesting that the DHCP server send its location. These are also many other uses for broadcasting messages, such as Address Resolution Protocol, ARP. However, broadcasting packets has certain disadvantages. If many broadcast messages are sent on the network, this places a burden on network devices. Even though many devices on the network do not need the broadcast packets, they still receive them, wasting network resources. Because of this, good network design should aim to reduce the size of broadcast domains, reducing the impact of this wastage. There are two currently used versions of IP, IPv4 and IPv6. The older IPv4, which is still in common usage, allows broadcasting. The newer IPv6 has eliminated the broadcast transmission altogether. To recap, switches work at the access layer. They allow terminals, servers, and other hosts to access the network. They carry out data frame switching and addressing. A single switch often corresponds to a single broadcast domain, which means that all nodes directly connected to a single switch are within that broadcast domain. If one node broadcasts data, all other nodes within the same broadcast domain will receive it. As well as broadcast, there are two other methods of sending data: unicast and multicast. In a network with nodes A, B, and C, when data is unicast from node A to node B, only node B will receive it. Node C does not receive the data. Similarly, when data is multicast, it is sent from one node to multiple nodes, but not to every node in the broadcast domain. We will look at how this works in more detail later. This is a Huawei switch. The basic function of a switch is to exchange data frames. It provides access to end-user devices and implements basic access security functions, such as MAC address filtering and ARP spoofing prevention. It also provides broadcast domain isolation using VLANs, Layer 2 link redundancy, loop prevention, and load balancing. Nodes or network elements connected to a single switch are typically in the same broadcast domain or LAN. A broadcast domain is a logical subnet. For example, the switch on the left side and PCs connecting to it comprise LAN 1, and the switch on the right side and PCs connecting to it comprise LAN 2. Pieces connecting to the same switch communicate at layer 2 as long as they are configured with correct IP addresses. However, devices on different LANs belong to different logical subnets and therefore cannot communicate with each other. To enable inner LAN communication, you need a layer 3 device, a router. The icons used in this figure are the standard ones used by Huawei. One of the functions of a router is to isolate broadcast domains. Each interface of a router corresponds to a broadcast domain. Different interfaces belong to different broadcast domains and different logical subnets. If you attempt to configure IP addresses on the same network segment for different interfaces of the router, an error occurs. Routers transmit data at layer 3. We will look at the differences between layer 2 and layer 3 data transmission later on. Routers also support routing protocols and maintain routing tables. The function of a router can be likened to that of a subway station in daily life. A data network with many routers is similar to a city's subway system with multiple interchange stations. The basic function of a data network is the moving of data from source to destination. This is like delivering a passenger from their origin to their destination. When passengers arrive at an interchange station, they look for the correct direction to their destination using a map. With a router, this decision is made by looking up the destination IP address in the routing table, finding the matching entry, and forwarding the packet over the corresponding interface. As the name suggests, routing is a basic function of routers. In order to use network resources optimally, routers must determine the optimal path to the destination address. Routers also have many other functions, such as modular boards, WAN access, network address translation, NAT, and security features. Externally, a router typically has fewer interfaces than the switch. As networks expand in size, more and more network devices are required. Similarly, the cost, features, and challenges to data communication also increase. We must test the performance of a variety of devices, features, protocols, technologies, and mechanisms, so that data communications engineers understand how the network works. As the technology becomes more advanced, network complexity is increasing. Networks are designed to meet customer service demands. Only by fully understanding the service requirements and configuring the network accordingly can network engineers create real value. Network topology is another concept that data communications engineers need to grasp. This network topology is a logical map of all of the devices and cables in the network. In the preceding slides, we have looked at the basic concepts and devices involved in data communications. We have already briefly mentioned the difference between layer 2 and 3. Now let's look in detail in the 7-layer OSI reference model. The OSI model is a reference model with 7 layers. Each layer has its own functional definition. OSI stands for Open System Interconnection. It is defined by the International Standards Organization ISO. It is a flexible, stable, and interoperable model. It is not a single protocol, but rather a model within which networks and the protocols they use can be understood. The OSI model specifies interconnection standards for different systems. For example, there are many different manufacturers that make network interface cards, and many different programs that transmit files using FTP. But all of these pieces of software and hardware must be compatible and able to interconnect. This system is fundamental to allowing the rapid development of communications networks. The OSI divides a networking system into 7 layers, starting from the physical layer, data link layer, network layer, transport layer, section layer, presentation layer, and application layer. In the following slides, we'll go through the functions of each of the OSI model's 7 layers. There are many advantages to the OSI model. It breaks up the complex process of communication over networks into simpler, more easily understandable processes. We can compare this to the different components of a desktop computer with the CPU, memory, line card, and so on. The CPU and memory may be made by different companies, but they must still be compatible with each other. To specialize in specific types of components, playing to their technological strengths, while still adhering to product standards which allow interoperability. This allows components to integrate seamlessly. The OSI model is similar in that it allows devices from different vendors to interconnect with each other based on shared standards and protocols. Let's take a look at the 7 layers of the OSI model. Starting from the lowest layer, they are Layer 1, the physical layer, Layer 2, the data link layer, Layer 3, the network layer, Layer 4, the transport layer, Layer 5, the session layer, Layer 6, the presentation layer, and Layer 7, the application layer. The physical layer consists of the binary digits, a series of zeros and ones being carried over physical media such as wires and radio waves. The application layer interfaces directly with human operators. Each layer in between, from low to high, is an increasing layer of abstraction, interfacing with the layers above and below it. Once you're familiar with the OSI model, you will be better able to understand the layer of abstraction at which each device operates. For example, routers typically operate at Layer 3, switches at Layer 2, and cables at Layer 1. Layer 5 to 7 are responsible for high-level functions. We call these the system layers. Layers 1 to 4, meanwhile, are responsible for transmitting the data from its source to its destination. These layers are responsible for data reliability, data corruption, data loss, and addressing. Each layer has its own function. The application layer defines application programs and protocols. These application programs are not software such as Skype, but applications such as Telnet or Hypertext Transfer Protocol, HTTP. You will likely already be familiar with HTTP from web addresses. For example, the Full Uniform Resource Locator URL of Huawei's website is http://huawei.com. This means that the information displayed on the page, such as text, images, and multimedia, has been sent using HTTP. Next is the presentation layer. This is responsible for determining the standards for displaying those pictures, texts, and so on. The session layer is used for setting up, maintaining, and tearing down sessions between nodes. These 3 layers are called the system layers and implemented by the system. The following layers are responsible for transmitting the data from its source to its destination. The transport layer provides reliable or unreliable end-to-end data transmission. The network layer provides data addressing and routing and supports routing protocols. It focuses on the source and destination of data. For example, the source may be a user's PC in China, and the destination may be a user's PC in the USA. In this example, data can't simply be sent directly from the PC in China to the PC in the USA. The data link layer is used to transmit the data between the individual devices involved. The type of link used may be varied. Some are Ethernet links, some are frame relay links, some are PPP links. The data link layer encapsulates data in frames, transmits it between individual nodes, performs error checks, and provides layer 2 addressing. Finally, at the physical layer, data is transmitted in bit flows over twisted pair cables, optical fibers, or other media. Each layer of the OSI model is fully responsible for the functions assigned to it, but upper layers are dependent on lower layers, and lower layers provide services to upper layers. Next, let's examine the basic content of each layer in more detail. The application layer is the highest layer. As we have seen previously, application programs such as HTTP can be distinguished from software such as Skype, browsers such as Internet Explorer, Chrome, and Firefox provide Internet access. When we browse web pages, however, the information is really being provided using HTTP rather than the browser. As well as HTTP, the application also includes some other protocols. For example, Telnet is used for remote login to network devices. FTP is used for transferring files. SMTP and POP3 are used for email. DNS is used for querying a domain name server to look up IP addresses of websites from their URLs. The numbers shown in the brackets are the port numbers used for each of these protocols. The data transmitted over networks is very often produced at the application layer. For example, when we access a website or download a picture or some text, this data is being transmitted using HTTP. Next, we have the presentation layer, which is responsible for the encoding and decoding, encryption and decryption, the compression and decompression of data. Commonly used presentation layer standards include ASCII for text and JPEG and GIF for images. The session layer is responsible for establishing, managing, and terminating sessions between presentation layer entities. In the TCP/IP protocol suite, the functionality of layers 5 to 7 in the OSI model are integrated into a single layer, which is often simply referred to as the application layer. Next is the transport layer. The transport layer is responsible for fragmenting and reassembling data and providing end-to-end transmission. There are two main transport layer protocols in the TCP/IP model, TCP and UDP. TCP provides reliable transmission, whereas UDP provides best effort transmission. In the next class of this course, we will be discussing these in more detail. Next, we have the network layer, which defines layer 3 logical addresses. In the TCP/IP suite, the most commonly used network layer protocol is IP. This is the most fundamental and most important protocol for data communications networks. It defines the format of IP data packets. For nodes to communicate properly over IP networks, each node must have a unique IP address. IP is not the only network layer protocol. However, with the development of communications technology over time, it has come to replace many of the other network layer protocols to become the most important and commonly used. IP is used for packet addressing, ensuring that the packets reach their destination, route selection, and maintaining routing tables. Network layer devices are typically routers. We have previously discussed the difference between broadcast, multicast, and unicast transmission. Each interface of a router corresponds to a broadcast domain. Aside from this, Routers can also perform packet addressing and forwarding, finding the optimal route to the target network. The aim of routing is to deliver the payload of the packet from its source to its destination. This is much like sending a letter using the postal service. The payload is like the letter itself, carrying the data that the sender wishes to convey to the recipient. When writing the envelope, the sender must include the destination address to ensure that the letter reaches its destination. In IP routing, the destination address is required, but so is the source address. In order to help routers learn where to send packets in the future, when the router receives a packet, it finds the destination IP address in the packet header and looks it up in its routing table. Once it finds a matching entry, it sends the packet to the next hop device by forwarding it out of the interface mapped to the IP address. In our postal service example, this is like different post offices sending letters to each other before they eventually reach their destination. Other than basic routing functions, routers can also carry out traffic management, connecting WANs and various other functions. Any node which needs to communicate on the data network must have a unique IP address. In our example of posting a letter, this is similar to the address of a house. House addresses are split up into house number, road name, city, and so on. Similarly, IP addresses are split into host, subnet, and network parts. Note that a single physical device may have more than one IP address. For example, if a PC has more than one network interface card, each network interface card can have its own IP address, but these addresses must be on different network segments. Similarly, a router with multiple interfaces has one IP address for each interface. Let's briefly revise the routing process again. A router or other layer 3 device receives an IP packet. It checks the header for the destination address, finds the matching entry in the routing table, and forwards it out of the corresponding interface to the next hop device. If there's no matching entry, the packet is dropped. Now, let's look at the data link layer. Data transfer at this layer is similar to taking a long train ride. Let's say that we are traveling from New York to San Francisco by train. To get there, we must travel through Chicago, Salt Lake City, and many other cities along the route. And at each of these stations, we switch trains. These points and the route we travel along can be seen as acting like the data link layer. At the data link layer, data from the network layer is encapsulated in frames. Header fields are written, and the encapsulated data is transferred. Flow control, error control, and access control are also happen at the data link layer. The data link layer provides services to the network layer based on the physical layer. There are many data link layer protocols, the most famous of which is Ethernet. An Ethernet can be understood as being made of Cat5 or Cat6 cables connected to a switch by RJ45 connectors. Though token ring networks can still be used to create LANs, they have largely been phased out in favor of Ethernet. Data link layer protocols for WANs include PPP, HDLC, and frame relay. At the data link layer, data moves along a link section by section. Each section of a link must have an address. If it is an Ethernet link, there needs to be a MAC address. MAC addresses function as hardware addresses. For example, the MAC addresses of a computer's network interface card. They are burned to the network interface cards before delivery. Unlike IP addresses, which consist of 32 bits. MAC addresses consist of 48 bits. The two types of addresses have similar purposes, but behave differently. IP addresses are typically assigned by an ISP or a network administrator, whereas MAC addresses come pre-assigned and cannot usually be changed. IP addresses, however, can either be static or dynamic, and as such are not permanent. Also, whereas IP addresses change depending on the network a device connects to, a device MAC address will remain the same. Therefore, an IP address is quite like a location address, whereas a MAC address behaves more like a name on the birth certificate. IP addresses are typically represented as 4 groups in dotted decimal notation, whereas MAC addresses are made up of 48 bits in hexadecimal notation. The first 3 octets identify the organization that assigned the MAC address and are known as the Organizational Unique Identifier, OUI. The following 3 octets are assigned according to the internal practices of the assigning organization and make up the device's unique identifier, known as an extension flag. By clicking Run and entering CMD ipconfig all, you can find your wireless network interface card's IP address, subnet mask, gateway address, and DHCP server address. The IP address is assigned by the gateway. In addition, this is where you will find the device's physical MAC address. In hexadecimal notation, the most common Layer 3 devices are routers. The most common Layer 2 devices are switches. The basic function of a switch is to exchange data frames. Each port on the switch acts as a single collision domain. Therefore, there is no chance of a collision between devices connected through different ports on the switch. The entire switch belongs to a single broadcast domain. When the single device connected to the switch broadcasts a frame, devices connected to any port on the switch can receive it. Switches facilitate these exchanges through the use of MAC addresses. The final layer of the OSI model we'll be covering is Layer 1, the physical layer. This layer is typified by physical media such as cables and interfaces, and is responsible for the transfer of each individual bit from hop to hop. Here are a few connection interfaces, with specific focus given to the standard RJ45 ports used on Ethernet networks. The 2 diagrams on this slide show the 2 common types of Category 5, Cat5, twisted pair cables. These 2 varieties are known as straight-through cables and crossover cables. Here we have pictures of common optical fiber connectors. SC and ST are the most common of these 4. The most common Layer 1 devices are hubs. All devices connected to a hub belong to the same collision domain, and so only one node can use bandwidth at a time. That is why hubs are rarely used on modern networks. This is the entire OSI reference model. In this networking example, PCA has an IP address configured. The gateway address is the IP address of the router interface connecting to PCA. So does PCB. How do A and B communicate? Let's suppose that B is the server and provides web services. A acts as a client to access B. This is A and B's HTTP data interaction process. Data cannot be sent directly and must instead have headers and sometimes trailers added at each layer. This process is called encapsulation. In this example, HTTP generates the payload at the application layer and gives it to the presentation layer and then an session layer. In TCP/IP, the top 3 layers are unified, so they simply send the HTTP data over the transport layer. The transport layer takes the HTTP data as its payload and encapsulates it with appropriate fields, including the source port number and the destination port number. This content is then sent to the network layer, which encapsulates the data from the upper layers with the source and destination IP addresses, as well as other fields. At the data link layer, the upper layer data is again encapsulated. PCA and the router are connected through a network cable and use Ethernet as a media. The data link layer adds an Ethernet header with the source and destination addresses. The source is the MAC address of PCA's network interface card. Does this mean that the destination is the MAC address of PC's network interface card? In this case, no. MAC addresses are valid only on LANs. The destination address is therefore the gateway MAC address. All of the data is turned into a stream of bits, for example, 1010, at the physical layer and is transmitted to the router through a network cable. After the router receives the bit stream, it begins the process of decapsulation. The router first examines the outermost header, which is the data link layer header, and finds that the destination MAC address is its own. Therefore, the router removes the data link layer header. The router then examines the IP packet header and finds that the destination IP address is server B's address, not its own. It then re-encapsulates the data with the source MAC address as its own interface's MAC address and the destination MAC address as that of PCB. Once PCB receives the data, it examines the data link layer header, finds that the destination MAC address is its own. It then looks at the network layer header and finds that the IP address is also its own. Finally, it looks at the transport layer header, finds that the destination port number is 80, signifying that it is HTTP data, which is then displayed in the user's browser. This completes the entire data transfer process. Here are a few concepts explained. The top layer data is the payload. Adding headers and sometimes trailers at lower layers is called encapsulation. Each layer has different protocol data units, PDUs. Transport layer PDUs are called segments or datagrams. Network layer PDUs are called packets. Data link layer PDUs are called frames. There is no real PDU at the physical layer because all data at this layer is simply sent in bits. The receiving terminal starts from the lower layers and moves up. First, it examines the frame header and decapsulates it. It then looks at the packet header and decapsulates it. Next, it looks at the segment header and then transfers the data to the corresponding upper layer application. This is the entire process of data transfer on TCP/IP networks.